We recently learned about the power rule, which is a shortcut to using the long derivative formulas to find derivatives of power functions. Mathematicians realized there were also other patterns to use for different types of functions. Our learning target today is to look at two more shortcut rules called the product and quotient rules, in which we'll compute derivatives of products and quotients. The product rule is used when we have a function that is the product of two different functions, and unfortunately we can't just take the derivative of each and multiply them together. Mathematicians realized the pattern was a little bit more complicated than that. You take each function and multiply it by the derivative of the other function, and then take the sum of those two products. That is a lot to digest and memorize, so I've been using a little trick that I learned when I learned calculus to help my students remember how to do it. So when we look at these two functions that are the product, which make up f of x, we'll name this function g of x left and h of x right, because visually it's the left function and the right function. So when I take the derivative of f, I'm going to take my left function and multiply it by d right, or derivative of the right, plus copy my right function and times it by the derivative of the left, or d left. So when we talk about the product rule and we are more familiar with it, we'll say to each other, okay, we need to do left d right plus right d left, which right now sounds pretty crazy, but it'll become shorthand pretty soon for us. So let's take a look at our first example. I went ahead and set up our product rule for f prime. So we start by copying our left function, which is x squared plus 3, and then we need to times it by the derivative of the right. And this is where we'll use the power rule that we learned recently. And we know that the first power will come down, the x will then be to the 0 power, so we'll get a 1 there, and then minus the derivative of any constant is 0, so d right ends up being just the constant 1. Product rule is always a plus in the middle, so you might want to emphasize that to yourself. It helps me think about product and plus both start with p. Then we copy our right function and times it by the derivative of the left function. And so power rule on the x squared gives me 2x to the first, plus the derivative of the constant 3 is always 0. So now I've got my left d right plus right d left, and we need to simplify. So we'll need to distribute our derivatives to the left and right functions, and when I distribute that constant 1, I get the same expression, x squared plus 3. Put my plus in the middle, and when I distribute the 2x, I get 2x squared minus 2x. I'll combine my terms and get a final answer. So f prime, the derivative of our original function f, simplifies to 3x squared minus 2x plus 3. Our second example doesn't look like a product at first until we think about what it means for a quantity to be squared, and it means it's being times by itself. So if we write that twice, we're going to see that we do indeed have a left and a right. They'll just happen to be the same function or expression. So I set up our function as the product of two of these binomials. You might have noticed that the question asked you to find dy over dx. We haven't seen that notation a lot this year, but we did learn that it means derivative, just like the prime means derivative. It's just a different type of notation. So we're still going to follow the product rule to find that derivative. So I went ahead and copied the left function, which is 2x cubed minus 4. When I take the derivative of the right, which happens to be the same function, we are going to use the power rule. The 3 comes down, multiplies that 2 coefficient, and we get 6x. Now to the second power, we need to subtract 1, and the derivative of that minus 4 constant is 0. And you might have already thought ahead and realized that our right d left is going to be the same exact thing as left d right, because we're dealing with the same two functions. So let's go ahead and copy that. When we do our distribution, we get 12x to the fifth minus 24x squared, and we'll get that twice, the exactly the same thing. And combining like terms, our final answer will be 24x to the fifth minus 48x squared to be dy dx, which is the derivative of our original function y. Just want to make one more comment before we move on and try the quotient rule. It says products may be simplified algebraically before differentiating instead of using the product rule. So what I mean by that is you could have algebraically FOILed these first, outer, inner, last, and gotten the simplified function and then taken the derivative of that using just the power rule, and you would get the same exact answer. So in those types of cases where the functions are easy to multiply out, you might find that that's a better route or alternative, but the product rule always works and we'll need it for more complicated functions. So it's definitely worth the practice. Next, we're going to learn about the quotient rule, which is the shortcut for finding a derivative when we have a function that's the quotient of two different functions. As you can imagine, this rule is a little more complicated. It does have some similarities to the product rule in that we will take one of the functions and multiply it by the derivative of the other. But here's where the differences start. Product rule had a plus. Quotient rule is a minus in between those two products. And it's also divided by another term, which is h squared. H is the lower function, g is the higher. So you might have noticed already that I've made a lot of notes here. So just like we have a trick to remember product using left and right, quotient, we definitely need a little help remembering this formula. So we're going to use high and low. So we take the low function, times it by the derivative of the high, minus the high times the derivative of the low function, all over low times low, or you can also say low squared. And again, this is very new to you, but pretty soon you'll be saying this fast just like me, and I'll say we need to do our low d high minus high d low over low low. And I tell students it always sounds like we're yodeling, but we get used to it, our little crazy calculus talk. Another thing I noticed over the years is that students often mix up which of these terms come first, and it's really important because there's a minus there. So commutative property says we can't mix those up and get it right. So I came up with this little visual that might help you. I hope it does. We need to start low and then do our d high minus high and then d low. So that tells you or shows you kind of the slope of low to high and all over low low. So let's take this crazy expression and try to apply it to our first example. So I set up our template for the quotient rule. I put in the functions that we know for sure. So we're going to start with our low function, which is 2x. Our d high will be the derivative of x squared plus 6. So using the power rule on the x squared, we get 2x. Derivative of plus 6 is 0. Quotient is minus in the middle. Copy your high function and times by the derivative of the low function. And 2x to the first gives us 2x to the 0 when we do the power rule. So we're left with just the constant 2. And low low is on the bottom, so 2x times 2x. You can do low squared. I have just found that many students have trouble if they're moving too quickly and they don't square the bottom correctly. So it's much safer from careless errors if you just copy the low low twice. So when we start to simplify, I usually simplify the denominator first because it's easier. So 2x times itself is 4x squared. Then we happen to have the same thing to start the numerator. That's just a coincidence. So we get another 4x squared. We have this minus. We need to be careful with how we deal with the distribution after the minus. Anytime you have more than one term that follows a minus, I think it's safest to put it in parentheses. So I'm just distributing the 2 to the x squared and the 2 to the 6. And then in my next step, I will distribute the minus to both of those terms. That's really important, especially that the 12 you remember to make negative. Now, if you do feel comfortable to distribute the minus and the 2 at the same time, you can. Just be careful of careless errors. So after I distribute the minus, I combine the x squareds on the numerator. I got 2x squared minus 12 over 4x squared. I noticed that all of those coefficients were even, so I'm able to pull out a 2. I wish I could have shown you that step. So I reduced all the terms by 2. So the final answer is x squared minus 6 over 2x squared. This next problem is, again, at first glance, you wouldn't guess right away that it was a quotient. But if you notice we have a negative 1 exponent on this 2x minus 1, that does put that expression in the denominator. And so we see now that it is a quotient. So let's practice our quotient rule one more time. So far I have low, derivative of high is 3 minus high times the derivative of low is 2 over low low. I distributed my 3, got 6x minus 3. And I just distributed the 2 here, keeping my parentheses on top. When I distributed the minus, I noticed that these 6x's would cancel. I had a negative 3 minus 10, so negative 13 is all I have left in the numerator. In the denominator, we don't have to square out, or I'll leave it like that.